In the previous couple of videos, we discussed performing the unshift operation, which basically used for adding the node in front of the single linked list, right? That means that in front of the existing head node of the single linked list, we are trying to add a new value or new node with the help of a unshift operation. Now in this video, let's try to understand a function which basically removes the node in front of the single linked list. That operation is nothing but the shift operation. So as part of the shift operation, what exactly we will do is we will basically try to delete the very first node that we have on the singly linked list. That means that we will try to delete the node that is available at head of the singly linked list. Okay, so that is the purpose of the shift operation. Here we will not be taking any arguments from the user. In the end, we will simply return the node that we have removed. That means that whatever the previous head node that we had, right, that we will return as a output. Okay, that is the functionality definition. Now let's just see what all are the different cases that can occur when we try to implement the shift operation. Obviously, the first scenario that could come is basically the singly linked list is empty. That means that there are no nodes at all on the singly linked list on which we are trying to perform the shift operation. And we know how can we check if the singly linked list is empty or not, right? We have made a separate video for that. If you haven't checked it out, you can check that out. But anyway, we know how we can basically check if the singly linked list is empty. If it is empty, obviously, if the singly linked list is empty, how can we actually delete the very first node, right? And head and tail will be at null or none based on our programming language that we are using for implementation, and length will be at 0. So obviously in this case we will not be able to perform shift operation or the removing the first node in the singly linked list. So we will simply return null or none. Okay, so that is the first scenario. And the second scenario is basically where we have only one node inside the singly linked list. If we have only one node in the singly linked list, right, we will have both head and tail node at the same node. That's why we have to make sure that whatever the only node that we are having, that itself we are deleting. That means that singly linked list is becoming empty. So to represent an empty singly linked list, what we will do, we will assign head and tail both with null or none. That's why here if we have only one node, update head and tail both with null or none. So null is basically for the people who are using Java or JavaScript, and none is for the people whoever is using Python for implementation. Okay, so that is something that we have to remember. Along with assigning, what we have to do, we have to make sure that length also we are updating it with 0, because whatever the only node that we have, we are deleting that. As a result, single linked list becoming empty, which is nothing but 0. The length has become 0. Here, before assigning null, you can actually read the head node, because in the end we have to return the node that we are deleting, right? So just for returning that node, before assigning head and tail and length with the appropriate values, make sure that you are reading the head value, so that in the end you can return that value, return the value of head, or you can return the node itself. Okay, that is based on your choice. Okay, this is the first scenario where we have only one node, and the third scenario is obviously greater than one node inside the singly linked list. In that case, what exactly we will do is we are trying to delete the very first node inside the singly linked list, right? So we basically have the impact on the head reference that we are maintaining inside the singly linked list, because whatever the node that is at the head, that itself we have to delete. To delete that, what we will do is whatever the next node that is there after the current head node, that node we will update it to the head of the singly linked list. In this way, we are basically losing the track of the previous head that we are having on a singly linked list. So simple operation, simple assignment operation. Here we have to delete the node that is at the head. That's why we will make sure that whatever the next node that is there from the current head, we will simply update that to head of the singly linked list. Because we are maintaining head and tail of the singly linked list, our head will be pointing to the node that is at the second position basically. In that way, from head to tail we still have the singly linked list, and whatever the node that was there previously as a head, that will get deleted. Okay, so that is the algorithm for removing the or performing the shift operation when we have more than one node. What we will do, we will simply update the head to the next of the head node dot next. Okay, that is something that you can simply do using a simple assignment operation. Along with that, we have to make sure that since we are deleting one node from the singly linked list, we have to make sure that we are decrementing the length by 1. So length will be length minus 1. Okay, so that is those are the scenarios that could come when we try to remove the very first node of a singly linked list. Okay, now let's just try to write the pseudocode for shift operation. Okay, so as part of the shift operation, our aim is to delete the very first node that we have on the singly linked list. Obviously here, what we will do, we will write a function called shift, and this function will not take any argument because it knows that it has to delete the very first node in the singly linked list. That's why we will not take any argument. So as part of the first check, what we have to do, we have to check if the singly linked list is empty. If at all, if the singly linked list is empty, we will simply return null or none based on the programming language that we are using for implementing. Okay, that is the first scenario. And the second scenario is basically we have only one node. That means we know the length of the singly linked list, right? Whatever the length that we are maintaining, if it is equal to 1, that means that singly linked list has only one node in it. Otherwise, the other comparison that you can do is basically if you have only one node, we will make sure that both head and tail are pointing to the same node, right? So the other comparison that you can do is head is equal to tail also you can do, because both will be at the same point, at the same node. As a result, they will match. But I tend to use the length based comparison for checking if the singly linked list has only one value or not. If at all, if we have only one value, what we will do, whatever the head node that we have, we will update it to null/none, and similarly we will also update tail node to null or none. Here one thing that you have to remember is none is for the people who are using Python for implementation, and null is for the people who are using Java or JavaScript for implementation. Okay, so that is something that you just have to remember. Anywhere I am using null or none, it is for the specific people, whoever is using the respective programming language like I mentioned previously. Okay, after updating head and tail, we will update length to 0, because whatever the only node that was there on the singly linked list, we have deleted that. As a result, the singly linked list has become empty. As a result, the length will be 0. So this is the case where we have only one node in the singly linked list. Now let's just try to handle the otherwise case where we have more than one node in the singly linked list. In that case, like I mentioned previously, what we will do, we will simply update the head with the whatever the next node we have from the existing head of the singly linked list. This is the head node and this is the tail node. Let's assume that we have 3 nodes on a singly linked list and we have to delete the very first node. So we will, if we want to delete, we will simply move the head to the next node. In that way, we will lose this, the head that we had previously. That's why we will simply update head with the head node dot next. Okay, and we have to make sure that we are decrementing the length also by 1. Okay, so that is something that you have to remember here. And couple of people, what exactly they will do is, here we already had the next node on the previous head, right? To make that also null, first what exactly they will do is they will read the current head is nothing but the head, right? Now on this, after updating the head node, what exactly they will do is they will also set current head dot next to null or none. Okay, so this is some optional operation, you don't have to do it, but just some people are very particular about updating the next to null or none based on our the way we are implementing. They will make sure they try to update the next of the whatever the head node that we had previously, because in the end we have to return the node that we are deleting, right? That is nothing but the current head. If we simply return the complete head, the complete node, using the next, user still has a possibility to traverse the remaining singly linked list. So they just don't want to give that functionality. As a result, before returning that value, they will make sure that they assign next to with null or none. In the end, we will simply return whatever the current head that we have inside the current head variable, which will basically have whatever the value we had at the head node in the singly linked list. Okay, so that is the implementation of a shift functionality on a singly linked list, which is basically used for removing the very first node we have on a singly linked list. Okay, now that we have written the pseudocode, let's go ahead and let's try to write the programmatic implementation of that. So inside the singly linked list class that we have written, I'll be adding a new called public. In the end, we need to return the node that we deleted, and the function name is shift. So this shift operation basically deletes the existing head node and updates the new the next node of the head node as a new head node, right? So basically here, since we are deleting the node in the singly linked list, there could be three situations that could come. One is either the linked list on which you are trying to perform shift operation, that could be empty, and the second scenario is either the singly linked list that you are trying to perform the shift operation can contain only one value, and the linked list, and third case is basically the linked list which can have more than one value. So if we try to write logic which can support these three cases, we are done with shift implementation. So basically the definition of shift operation itself is like it will delete the very first node, that is head node, right? So what we will do is we will simply write the logic for each and every case. So first case is basically trying to perform shift operation on an empty singly linked list. So on an empty singly list, how we will check? We will basically check if this dot head equal to null, right? But besides this, we've already used this check in most of the cases, right? Now let's try to use this dot length equal to 0. If the length of the linked list is 0, that means the list is empty and we can't perform any deleting of a node because there are no nodes at all. So in this case, I'll simply return null. Okay, so we have handled the first case where we are trying to perform the shift operation on an empty singly linked list. Now let's try to write the second scenario where we have only one node. So how will we know there is only one node? We can either check if both head and tail are pointing to the same node, or we can check if the length of the linked list is 1. So you can write either of them, but in this approach, just to maintain the difference in different ways of comparison, and previously we have already written if this dot head equal to this dot tail also, right? Now in this video, let me just use the length. If this is the case, we need to delete the head or tail, which is the same node, right? So there is only one node, that node also we need to remove. Since we have to return the node that we are deleting in the end, I'm reading it. So let me just read the value as current node equal to this dot head. Okay, once I read it, I have the access to the head node that we are going to delete. So since we are deleting the only node, all the head and tail should become null and length should become 0. So I'll simply update this dot head to 0. I'll also update this dot head to null, and I will also update this dot tail to null, and I will make length as 0. Okay, in the end, the node that we deleted is basically the head. or the tail which is same, because there is only one node in the linked list. So we'll simply return current node value that we have here. Now we have successfully written the shift operation for the two scenarios, where the first scenario is linked list is empty and the second scenario is where there is only one node in the linked list. Okay, now if none of these cases are matching, that means we have more than one value in the linked list. In that case, what we have to do, we have the current head node, and from the current head node we have to move on to the next node. That should be the new head node, right? And we have to make sure that we are deleting this value by updating the next to null, so that we can return that value and we can access the remaining linked list from head to tail once again. So how will we do that? For that, let me just read the values current head. This is nothing but this dot head. Okay, and next head value will be next node of the current head node. That is, let me just say next head, it is equal to current head dot next. Okay, so this next head will be the new head node after deleting the current head node. So I will simply update this dot head equal to next head. Okay, we can simply update the next of current head dot next to null. Okay, even if you don't do this operation also, it's fine, because we are anyway using head and tail only. Since singly linked list is only one way traversal is possible, right? So you will anyway not be able to access the node that is previously head. So even if you do this or don't do this, it's absolutely fine. And ultimately, since we are deleting the node from the singly linked list, the length will decrement by 1, right? So this dot length equal to this dot length minus 1. Okay, in the end we need to return the node that we have deleted, which is nothing but the current head. Okay, now let's go on and execute this line of code, this function, and see if it is actually working. Let me just comment out this unshift operation also for now. Okay, here we have 4 values in the singly linked list. Okay, if I try to perform SLL dot shift, basically it should delete the head node. That is, 10 is the head node in the singly linked list right now, right? So it should delete 10, and the resulting list should contain only 3 values, which are codingpal.r, true, and 10.0. In the resulting list, the head node will be codingpal.r and the tail node will be 10.0. Let's execute it and see the result. Run as Java application. If you see here, we have got 3 values only in the result list. As part of the last print statement that we have here, head node is codingpal.r and tail is 10.0, and the number of nodes we have is 3. Similarly, let's try to perform the shift operation on a linked list which has only one value. Here, since we are trying to delete the only node, right? If we try to read dot value, we will basically get the null pointer exception. That's why I'm just removing the dot value here. And if I execute it once again, the resulting list should contain 0 values, and head and tail both should be pointing to null, and the length should be 0. Okay, as part of the shift operation, we've deleted the only node that we have in the linked list, and as a result, traverse operation did not print anything. In the end, we are printing the head, tail, and length, right? So we have got the null, null, and 0, indicating that both head and tail are null and length is 0, which is nothing but the list has become empty. Now, similarly, if I try to perform shift operation on empty linked list, obviously we will not be able to perform anything, right? We will simply return null itself. So we can simply, if we run it, ideally it should print the same thing, null, null, and 0. Okay. In case if you want to capture the result here, node result equal to shift operation, whatever the value that we are returning as part of the shift operation, right? I mean, if you want, you can capture that and you can use that value in your further implementation in your actual projects. Okay, this is how we are actually implementing the shift operation, or deleting the very first node in the singly linked list and maintaining the consistency across the singly linked list again for the further operations. Okay, now that we have implemented the shift operation on a singly linked list, let's just try to analyze the time complexity and space complexity of the same. So you might be wondering, what is the best case and what is the worst case of implementing the shift operation, right? When we try to perform the shift operation on a singly linked list, there will not be any best case or worst case, because we are trying to delete the very first node on the singly linked list itself. Because even if the singly linked list has n number of nodes, even if the singly linked list has only one node, the operation is very similar. When we had only one node, we will simply update the head and tail and length with appropriate values. Even if we have more than one node, or even if we have n nodes, we will simply update the head node to the next of the current head that we are having. So obviously, be it the singly linked list where we have only one node, or be it the singly linked list where we have n number of nodes, we will simply delete the very first node by using the simple update operations. As a result, the time complexity will be order of 1 only. Okay, so now let's talk about the space complexity involved in performing the shift operation. So if you remember, we have basically defined a variable called current head, right? Where we tried reading the head node. Besides this read operation, and we after this read operation, we have basically updated the head node with the head node dot next that we already had inside the singly linked list. The only memory that we are consuming is for this variable where we are trying to read the head node, so that in the end that node is getting deleted, right? Basically we have to return in the end. So obviously that variable will take only constant amount of memory. And even if you take the scenario where we have only one node also, we are updating the head, tail and length that we are maintaining. We are updating it with the appropriate values with null or none and 0. So those update operations will take only constant amount of memory for implementation, right? So even if the singly linked list has only one node, even if the singly linked list has n number of nodes, whatever the shift operation that we are trying to perform will take only constant amount of space for implementation. Okay, that's all there is in terms of time and space complexity analysis of a shift operation on a singly linked list. Okay, so thanks for watching. I'll see you in the next functionality implementation.